The final topic we cover is nonparametric spatial covariance function, and we'll only cover it fairly superficially because this is very technical material, very mathematical. But it's important to know that it's there. It's a totally different perspective in that in a nonparametric approach, there is no model and the data suggests a particular functional form. So how does that work? It works by thinking of the autocorrelation, the sample autocorrelation at any particular location between any pair of locations, I should say, as a very general function of the distance that separates these. And the form of the function is not pre-specified. For example, later we'll see in geostatistics a very similar approach in that there is a function of the distance that separates the 2 points, but that function is specified, like, negative exponential, it has a specific functional form. In this case, it does not. One catch, though, is that the result is not necessarily valid in the sense that the covariance function must be positive definite. Okay, so what does that mean? You can think of a variance. A variance is a square. It's a sum of square deviations scaled by the number of observations. So that cannot be negative. So if you have, some kind of a function that ends up with a negative value for the variance, that's not valid. That violates some basic logic. Now, in a multivariate context, it's a little more complicated because the variance is not a single value, but it's a whole matrix, a variance-covariance matrix. And that matrix must be positive definite. So the elements of that matrix are the results of our nonparametric covariance function. And it can be, and oftentimes it is, the case that the data come up with a covariance function that isn't valid in the sense that its variance-covariance matrix is not positive definite. So that's a drawback of letting the data suggest a functional form. So how does this actually work? We conceptually look at each pair of observations, let's say I and j, and look at the cross product of their values in standardized and deviations from the mean, scaled by their variance. So that's very much the notion of a covariance, a generic notion of a covariance. So in practice, we can't do this because there are, for each pair, there are n squared minus n such pairs, and we only have n observations. So that's the problem, the incidental parameter problem. So instead, we're going to work with an approximation where we're going to try to locally, within a given distance range, estimate the sample covariance just for that subset of the data. And we're going to relate that to the distance that separates these points. So we're going to have, a distance band, say 0 to 10 miles. We take all the points, the pairs that are 0 to 10 miles apart, and we use those to estimate this covariance function. And we don't impose any functional form, but we fit a function through these values that is a flexible function of distance. Now, one approach is to use a kernel estimator. We talked about kernels before. It's a way of smoothing the neighboring observations. Some people use a spline as a very generic fit through these things. We won't get into these technical details. Just to give you a sense of how complicated this gets, here's a classic article where this approach was actually suggested by Hall and Patil. The kernel estimator is for a given distance, we have a kernel function of that basically takes into account, you can't see this in the expression is k dij over h and then the cross product. The k is actually a weight, and the weight is a function of the distance between I and j, with a smaller weight as the distance increases. That satisfies distance to k, and the h is there as a bandwidth cutoff. So some kernel functions, for example, a triangular one, have just a linear decay with distance up to the bandwidth, and then beyond that it's zero. Others are continuous, like a Gaussian kernel. So the distance keeps going, but after a certain distance, typically a function of the variance or the standard deviation of the Gaussian kernel, the weights are minimal and for all practical purposes are zero. So this is a weighting of the cross products. The cross products that are closer together have a higher weight than the ones that are further apart. And we pick a particular kernel function, as I mentioned, like a normal function or a Gaussian kernel or a triangular kernel or even a uniform kernel with a given bandwidth. And in the literature on kernel estimation is huge, and we don't really have the time to get into this. Important to remember is that the bandwidth is the critical factor. And as you can imagine, the smaller the bandwidth, the spikier the fit is going to be. The larger the bandwidth, the smoother the fit is going to be. The function used for the kernel itself does not seem to matter that much. So the Gaussian kernel is a very common use, in fact, in many software implementations. So how does this work then? We have the cross products, typically expressed in standardized form, so you don't have to worry about the variances. And we fit a generic function of the distance on there, on these cross products. It's a local regression, and as I mentioned, it depends on the bandwidth and the kernel function. The problem, as I mentioned earlier, is that the values of this estimated function do not necessarily have a valid variance covariance matrix. And for example, you might see that if the slope is positive or things of that nature. So in practice, we have implemented this in GeoDa in a very simple form. There are many different practical decisions that have to be made to fit these curves. We'll go over that in the lab exercises, but it looks something like this. This is for the price, the house prices again. We're taking the full distance range and we estimate these covariances in bins of distances. So for each bin, we have an estimate of the, since they're in standardized values, they're actually parallelograms, an estimate of the spatial autocorrelation. So for example, for the first bin, which goes from 0 to 4,800 feet, that is, we have an estimate of 0.2 as the spatial autocorrelation. So this is something that you can, in GeoDa, you can hover over each of these dots and find out what the spatial autocorrelation is. The bars represent how many pairs of observations are present in the bin, and we want to look out for bins that have too few observations. This is not a problem here. Even the smallest bin at the very end has 75 pairs in it, so we don't have to worry about this. The rule of thumb is typically 30. What we're interested in here, besides the value of the autocorrelation, is the point where the line crosses the horizontal, which gives us a measure of the range of spatial autocorrelation. As we go too far for larger distances, the autocorrelation should be ignored because it's often switches from positive to negative, and it also, for large values, it's really should be zero according to Tobler's law. So as I mentioned, there are a lot of practical decisions that have to be made in the construction of the parallelogram, such as whether we use the full distance range or cut off at a particular distance value. Here, for example, we take 20,000 feet maximum, and we also change the number of bins, and we get a much more fine-tuned measure of the evolution of the spatial autocorrelation, but the measure of the range of interaction is pretty much the same. We go through this in detail in the lab. So the upshot of is the use of the nonparametric approach. It gives us a measure of the range of spatial autocorrelation, which the traditional Moran's-I and Geary-C really don't do. That's more of an all or nothing approach. You don't have to specify spatial weights. Of course, you do have to specify a distance metric. The measures are sensitive to the fit of the kernel, and they may violate the positive covariance rule, and they also may violate Tobler's law. It's actually quite common to see an autocorrelation that increases with distance, which is in direct violation of Tobler's law. Now, why would this happen, you might ask? It happens typically because one of the assumptions underlying the analysis is violated. And the most common one is the one of a common variance. One basic assumption underlying all of global spatial autocorrelation analysis is that the variance is constant throughout. And if the variance is not, then it could very well be that, well, for one, the estimates of autocorrelation will not be proper estimates, so then you can get weird things like autocorrelation that increases with distance. So this concludes our discussion of global spatial autocorrelation. Next is local spatial autocorrelation and cluster detection.